Hello dear friends, we continue our discussion on layout design and we were talking about construction and improvement algorithms. In the previous video tutorial we talked about the construction algorithms in layout design. We talked about the graph-based method initially, then we talked about the core lab and ALDEP procedures. If you remember, the basic steps in a construction algorithm was to select a department and then place that department to somewhere in the design. And the basic difference between the construction and improvement algorithms is a construction algorithm starts from scratch. So initially there are no feasible layouts that you can use in your hand, and starting from this, scratch, after following the steps of the algorithm, you come up with a feasible design and in good quality, better, let's say, good, but there's no guarantee of optimality, of course, design. In improvement algorithms, in contrast to this, you start from an initial solution. You already have a feasible layout, and after following a number of steps, a number of moves, you end up with a better design, better solution. Okay, so this is the basic difference of a construction algorithm from an improvement algorithm, and in this lecture we will talk about improvement algorithms, their basic steps, and a number of examples. So let's start. So we already talked about construction algorithms. We learned the graph-based method. We learned the core lab and ALDEP procedures. And today we will talk about the improvement algorithms. Okay, and we will talk about a simple pairwise exchange method. We will talk about the craft algorithm, and we will talk about the microcraft, or shorthand MC craft algorithms. In improvement algorithms, what we do is we are given an initial layout. Okay, so this layout is given to us as a block layout. We know now what a block layout is. In the block layouts, the departments are represented by blocks, and they need to satisfy certain shapes. We talked about the feasibility rules of departments, and in order to represent the departments and the layout in our in the computer, we represent them with smaller unit area squares and represent each one of them with a number. And in fact, at the end, we come up with a matrix and we give this matrix to the computer. Okay, so we have such an initial layout, and also we know how to calculate our objective function, the rules of calculating the objective function. Whether it can be an adjacency-based scoring or distance-based scoring, we know how to calculate it. What we do is we modify this initial layout so that at the end of the algorithm, the final layout, the resulting layout, has a better objective function value. This is the whole objective of improvement algorithms. Get an initial layout, make some modifications on it, and come up with a better layout. So for this purpose, the algorithm makes some moves. Okay, it moves the departments around the block plan. You can think about this as a jigsaw puzzle, but there is an important difference. In jigsaw puzzle, the shapes of the pieces are fixed, so you just move them around the shape. But in layout design, while moving the departments, the blocks around the layout, you can also play with their shapes. Okay, so it can be a rectangular shape, then you can convert it to an L shape. It can be an L shape, then you can convert it like a T shape. Okay, so this changing of the positions or the locations of the departments as well as their shapes gives you too many degrees of freedom, too many things to play with, and as a result, the total number of alternatives that you have at the end is too much. Okay, and it takes a lot of time even for the fastest computer to evaluate all possible alternatives. That's why most of the improvement algorithms limits these kinds of chains. Okay, they do not allow all possible changes. They just search around only the allowed changes. Okay. In the previous lecture, we talked about the general steps of a construction algorithm, and it was basically repetition of two steps. The first step is the selection of a department, and the second step is placing that department. And we do this again and again until we place all departments. Like that one, we can also talk about the general form of an improvement algorithm. And in this one, what we do is, again, for several times, okay, we choose a pair of departments, okay, so we already have a layout, and from this layout we choose a pair of departments, and then we make an estimation of the effect for changing their locations. So we have department A and department B in the layout. We select these two departments, and we want to change their positions, their locations. And for this, we first estimate, okay, is it beneficial to change these or not? If you first make the change and calculate the objective function, exact optimal objective function value, it may take a longer time in computer. Instead of calculating the exact objective function, what the computers or what these algorithms do is they estimate the effect in a quick and easy way. They estimate, okay, is it beneficial or not? And if they see that it will be beneficial, then they make the exchange. Otherwise, they don't exchange these departments and go for another pair of departments to understand if exchanging them will be beneficial or not. Okay, and then when they make this exchange, at the end they check, they calculate the exact optimum and try to understand if the estimated value was correct, so that the new layout is better or not. Of course, if the new layout is not better than the previous one, they return back to the previous one. Okay? And we repeat these steps, choosing, estimating, exchanging, and checking steps until no more improvements are possible in the layout. Okay? So this is the general steps of an improvement algorithm. Do not be confused with this statement, because this is a heuristic algorithm and it doesn't guarantee optimality. But you may ask, okay, there are no more improvements, then it should be optimum. But the thing is, remember, we started with an initial solution, and over this initial layout we make these exchanges, and at the end we came to a layout where exchanging the departments will not give you any improvements. But if you started from a different initial solution, then make these exchanges, then you may end up with a different and a better layout. Okay, so depending on where or what kind of initial layout you started, you may end up with a different solution. That's why this is a heuristic and it doesn't guarantee optimality. So now we will talk about these steps, general steps of the improvement algorithm one by one. The first step was choosing a pair of departments. Okay, so how can we choose a pair of departments so that we can exchange their layouts? And this type of exchanging the positions of two departments may disturb the layout, the shapes. Okay, that's why two conditions must be satisfied while selecting these pair of departments. The first condition is the departments must have the same area. Okay, if two departments have the same area, then we can exchange their positions. And remember, in our block layouts, the areas are represented by square unit squares. Okay, so if two departments have the same number of unit squares in the layout, then we can exchange their positions. Now let's look at this example. So here, department A has this shape, and department C has this shape. Look. and we want to exchange their, let's say, positions. So is it possible to make this exchange? In order to understand this, let's count the number of unit squares. 1, 2, 3, 4, 5, 6, and 7. So A has 7 unit squares. 1, 2, 3, 4, 5, 6, and 7. C also has 7. Now I can exchange their positions, and when I do it, I will end up with this new layout. Look, now instead of A here, I have C, and instead of C here, I have A. So this is what we mean by exchanging the positions of the layout, okay? And if, for example, in this layout, A has 7 unit squares, but C has not 7, but let's say 10 unit squares. And if we want to exchange their positions, what would happen? So I would take these 10 unit squares and try to fit them to these 7. And it's not possible. So, and we know that we cannot have a layout with 7 unit squares here and 3 squares here, so that the total is 10, because they are disconnected. Remember the connectedness rule of the layouts, okay? So in order to not to disturb the departmental shapes, the first condition is to have the same area. And in this example, since A and C has the same area, we can exchange their positions. The second condition for selecting or choosing the pair of departments is these departments must share a common boundary. For example, look at this shape. Department A has this shape, and department B has this shape. So these two departments share a common boundary, okay? From here or from here, this is the boundary. And then if they share a common boundary, then we can exchange their positions even if the number of unit squares of the departments are different. Because what we do, again, since they share a common boundary, we will use the total of these two departments, total unit squares of these two departments, to come up with this new layout. So what we do, we initially delete all these A and B's. Okay, so again, sometimes we represent the departments with numbers, and we input these numbers into the computers. But in some examples here, we will use, instead of numbers, we will use A and B's. So that's basically the same thing. Okay? So don't be confused. So what do? We initially erase all A and B's in this layout, and then we start with this larger size department and start with the there are in fact two methods, either following a row sequence or a column sequence. Okay, we start with the corner of the other department and start placing B's. Okay, so in this one we use a column-wise serpentine layout. So we start with placing B to this corner, then to down, then to right, then to up, then to right, down, 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 and then this is the position of A. Then we continue with B and B and B here. Again, for the remaining part, we place the A's. Or we can use a row-wise serpentine layout, and in that case, what do? Again, we start from here, first move to the right, and then go to the left, and then until we finish all placing all squares of B. And then for the remaining one, we place A's. You see, starting from this one, if we exchange their positions, we may end up either with this one or this one. And the final layouts are not exactly the same as, changing the shapes of the departments, because their area requirements are different. So the shape of the departments are changed a little bit in this case. In the previous one, if they have the same area, then the shapes of the departments are exactly the same. But when they don't have the same area but the departments share a common boundary, then the departmental shapes can be changed a little bit. But you see, in this shape basically A was on the left and B was on the right, and here you see B is on the left and A is on the right, and on this one again B is on the left and top and A is on right and bottom. Okay, so this is how we perform the exchange operations in two of these cases. Basically, we have these two requirements for selecting the pair of departments. So after choosing the pair of departments, of course, we will make estimation. We will talk about that estimation later on. But we have this exchange operator. And in this exchange operator, we want to exchange with respect to the rules that we talked in while choosing these departments in order to reduce the total cost, okay, in order to improve our objective function value. But as we could see in the previous example, when the areas of the departments are not equal, there are many possible methods for exchange. And the shapes, the departmental shapes, the resulting layout depends on the method, how we filled in the unit squares of these departments. So in the previous example, we have just seen two possible ways, but in fact you can end up with many different alternative ways to do this. Okay? And sometimes this exchange operator may lead to the violation of shape ratio or corner count rules. Okay? So remember those rules. Other than the contiguity and connectedness rules, we also had this shape ratio and corner count rules. And when you exchange two departments with different shapes, with different sizes, one of the departments may have a larger number of corners, and the final layout will not be a good one, practical one. So in that case, you can manually adjust the departmental shapes at the end of the algorithm. So another procedure in this improvement algorithm is the estimation, as I told you. And why do we make this estimation? Basically, remember, in improvement algorithms, we want to make the layout better than the previous one, the initial one. And how do you define a better layout? You need to calculate an objective function value. Remember, we talked about adjacency-based scoring and distance-based scoring, right? So what are they? They are, in fact, our objective functions. For example, in distance-based scoring, we want to minimize the total distance multiplied by the flows of the departments, right? So when you have your initial layout, you can calculate the total distance of total objective function value of that layout. And after every change, you need to understand whether that change is beneficial for you, improves your objective function or not. One method to do this, of course, to calculate what happens exactly. But as I said previously, it may be very time consuming. But still, we want to know the effect of the exchange. Is it desirable to make this exchange or not? And since the original calculation of the objective function exactly takes a lot of time, what we can do is we can use a method to estimate the objective function, an easy method to estimate the objective function. So one method that the Craft algorithms does for this estimation is to assume that the centroids of the departments are not changed after the switch operation. But in fact, if the departmental sizes are different, then the centroids would definitely be changed. But in order to calculate the new centroid, identify the new centroid, then you need to make the exchange, find the final shape of the department, then find their centroid, and then make the calculation. But since, as I said, this will be time consuming, what we do, we assume that the centroids does not change. We easily calculate the objective function, estimate the objective function, and try to understand if this change is beneficial or not. But the thing is, actually, after you make this exchange, you may see that the estimation was wrong, and it's not beneficial to exchange these departments. But still, this estimation procedure uh, fastens the algorithm, makes the algorithm work faster. Okay, since we make an estimation, and let's assume that we make an estimation and we see that it's beneficial to make the exchange, then we make the exchange of a pair of departments. Then at the end we need to identify, we need to check if the exchange was really beneficial or not, if our estimation was correct or not. Okay. So we use a check procedure after making the exchange. For this purpose, as I said, we need to use a scoring model. It means that we need to calculate an objective function value, and this objective function value may depend on the distance relationship, so it can be adjacency based or distance based, and etc. Also, in fact, you can use more complex objective functions, more complex scoring methods, because in adjacency based and distance based scoring that we have seen until now, we didn't consider the type of material handling device. But if you already know the material handling alternative that you are going to use, then you can utilize these material handling alternatives and their associated costs and calculate more realistic objective function values. It's also possible. So we will first consider the pairwise exchange method as the first improvement algorithm in this video lecture. Okay. We will talk about craft and microcraft in the following video lecture. Pairwise exchange method is a simple improvement algorithm. Okay, we can use this pairwise exchange both with adjacency-based or distance-based scoring objectives. It's possible. But there's one limitation. We can apply this pairwise exchange method for layouts with equal area departments. Okay, if the areas of the departments are equal, then we can apply this procedure. And what do we do? Since the areas of the departments are equal, it means that according to our previous discussion on the rules for choosing departments, one rule was if their areas sizes are equal, then we can exchange them. Okay, so what do we do? In this case, we can exchange any pair of departments. It's possible, right? So what do we do? For a given initial layout, we consider all feasible exchanges of the locations of these departments. We evaluate their values, and then we select the pair of departments that provides us the largest reduction in total cost. Okay, this is called steepest descent. So there may be multiple alternatives that provides a reduction in the cost, but among these multiple alternatives, we select the one which provides the largest reduction, and this type of algorithms are called steepest descent algorithms. Okay. So in fact, in this algorithm, we don't need to make an estimation because calculating the original cost is as easier as calculating the estimated value, because since the sizes of the areas of the departments are easier, already their centroids will not be changed after the exchange. Their centroids will be the same. So the original or the exact objective function value will be equal to the estimated value in this case. Let's first consider the steps of the algorithm, then we will make an example, and with the example it will be more easier to understand. So what are the steps of the algorithm? The first step is to compute the total cost under the current layout. Okay. So as we said, this is an improvement algorithm. You start with an initial layout. It's given to you, and the first thing to know is what is its objective function value. Calculate this objective function value. Let's say that this objective function value is TC current. Okay. Then we consider all possible pairwise exchange alternatives for this given layout, and then compute the total cost after each exchange alternative. Okay. We try each exchange alternative one by one and calculate its total cost value. Then we select the exchange alternative with the minimum cost that we had from step 2. Then we compare this minimum cost with the cost of the original layout. Then we have two cases. If this minimum cost of the alternative layouts that we identified in step 2 is less than our original cost of the layout, then we make the exchange, change our current cost to this minimum cost, and then we go to step 1 to repeat the same things with the new layout. Okay. So as long as we have an improvement, we repeat these steps again and again. Otherwise, if the minimum, even the minimum cost is larger than the cost of my initial layout, then we stop the algorithm. So these are the steps of the algorithm. So let's see, let's make an example on this. Assume that we are going to lay out 4 departments in such a shape. Okay, so each department has the same size. So pairwise exchange works in this case. Department 1 is placed here, 2 is here, 3 is here, and 4 is here. And total shape of my layout is something like this. Okay, this is just for illustration purposes, a simple example. The flow between each pair of departments is given to us in this matrix. So these are departments 1, 2, 3, 4, 1, 2, 3, 4, and these are the flows over here. So the flow from department 1 to 2 is 10 units. Okay, 1 to 3 is 15, and 1 to 4 is 20. Okay, these are given. And from this layout that's given to us, we can calculate the current distances. So in order to calculate distance-based objective, remember what we do. We multiply the distance between department 1 and 2 with the flow between departments 1 and 2, and multiply this with the cost of transferring 1 unit of item for 1 unit of distance, and that cost in this example is given as 1. Okay, so the cost in this example is 1. So basically we will multiply the distance between the departments with the flow, and for that purpose we need the distance between the departments. So let's calculate this distance. Okay, calculating the distance is easy because it's a simple example, and you see the distance between the departments are the distances from centroid to centroid. Of course, it may be asked to use a rectilinear distance or Euclidean distance, but since this is a simple example, the rectilinear and Euclidean distances are the same for this example. Basically, we will calculate the distances from centroid of one department to the centroid of the other department. And the centroid of the first department is here, and centroid of the second department is here. And their distance between the distance between department 1 and 2 is this one. Okay, so this is a unit area square. We can assume that this distance is 1. So it means that this distance is also equal to 1 because we have 1/2 from here and 1/2 from here. When we add it up, it's 1. So the distance from department 1 to department 2 is 1 unit. And it's symmetric. From 2 to 1, we have the same distance. That's why from 2 to 1, the distance is also the same. What about the distance from 1 to 3? The centroid of 1 is here and centroid of 3 is here. Since they lie on the same line like this, the Euclidean distance is equal to the rectilinear distance. It's only for this example. Okay? And what is this total distance? We have a half here, 1 here, sorry. Is this one? We have 1 here and we have another half here. So the distance from 1 to 3 is 2 units. And since it's symmetric, 3 to 1 is also 2 units. Okay. So in a similar way, we can calculate the distance from 1 to 4 and it will be 3. 4 to 1 will also be 3. So we will calculate the distance from 2 to 3, which is 1, 2 to 4, which is 2, 3 to 4, which is 1. So this is the distance matrix for this given layout. So when you have the layout, you can obtain the distance matrix easily. Now, how do we calculate the total cost of this initial layout? Basically, we will multiply the flow with the distance and with the cost, which is 1, and we will sum up all these multiplications. So, in fact, we are multiplying the flow matrix, each entry of the flow matrix with the corresponding entry of the distance matrix. Okay? So the flow between 1 to 2 is 10. Distance between 1 to 2 is 1, so it's 10 times 1. Plus, the flow between 1 and 3 is 15. Distance between 1 and 3 is 2, so it's 15 times 2. Then 1 to 4 flow is 20, distance is 3, 20 times 3. Then we have this 2 to 3, 10 times 1. Okay. 2 to 4, it's 5 times 2. And 3 to 4, it's 5 times 1. And we continue, in fact, because the flow between 1 to 2 can be different than the flow between 2 to 1. So what do we do? 2 to 1, 0 times 1. But since you see here, since all these flows are 0, all those multiplications are 0. Okay, so that's why we don't write it. And in total, the total cost, distance-based score of this initial layout 1, 2, 3, 4 is 125. This is what we call TC current, our current cost. We'll start with this one. Now let's consider exchanging the departments 1 and 2. Okay, so initially remember it was 1, 2, 3, 4. Now we have 2, 1, 3, 4. We exchanged their positions. In fact, we didn't exchange. We just trying this. Okay, we try what happens to the total cost if we make this exchange. Of course, when you make this exchange, the flow matrix will not change. We will still have the same flows between department 1 and 2, 1 and 3, and etc. But what is going to be changed with the change of the positions is the distance matrix. Okay, so now we need to calculate the new distance matrix, and how we can calculate it is it's in fact easy. Now again, we will calculate the distance from the centroid of department 2 to 1, which is 1, right? So the distance between 1 and 2 is 1. What about distance between 1 and 3? So it's also 1. But remember, initially, when department 1 was here in position of 2, the distance from 1 to 3 was 2 units, right? What about the distance from 1 to 4? So from here to here, the distance is 2 units. Good. What about the distance from 2 to 3? It's 2 units. And 2 to 4, it's 3 units. Okay, these distances are changed. And the distance between 3 to 4 is 1 unit. Okay, And this is symmetric. It means that we will have exactly the same values in the lower corner. So the distance from 2 to 1 is 1, and etc. We can fill in all of them. But since the flow matrix, the flow values here are all 0, we will not need the distances here. We will not use those. Okay, let's calculate now the new cost value. What we will do is we will multiply the flow with the corresponding distance. Okay, so the flow between 1 and 2 is 10, and the distance between 1 and 2 is 1. Okay, the distance between 1 and 3 is 15, and the flow between 1 and 3 is 15, and the distance between 1 and 3 is, the new distance is again 1. What about the flow? The flow between 1 and 4 is 20, and the distance between 1 and 4 is 2, so we will have 2 over here. Then the distance between 2 and 3 is 10, and the flow is 2, so it is 10 times 2. Okay, then the distance, flow and distance between 2 and 4 are 5 times 3, so this is 3. Okay, what about 3 and 4? It is 5 times 1. Okay, so this is 5 times 1. And what we obtain in total when we add this up is 105. Remember, our initial layout's total cost value was 125. The new value is 105, which is better. But the algorithm does not immediately make this exchange. It needs to try all possible exchanges. So this is the exchange between departments 2 and 1. So initially we started with 1, 2, 3, 4. And in this case we tried replacing it with 2, 1, 3, 4. But we have other exchange possibilities as well. So for example, from here we could exchange 1 and 3, we could exchange 1 and 4, then we could exchange 2 and 3 and 2 and 4, and we could exchange 3 and 4. So we need to try all of these exchanges and calculate the objective functions of all of them, and then select the one with the minimum cost. So there may be another alternative with a lower cost than this one. Then in that case, we will not select this one, but we will select that alternative. So let me give you the values of other exchange options. So we continue the calculation in the same way. So remember, we started with this initial layout 1, 2, 3, 4, and we calculated the total cost of this layout as 125. So this is our TC current layout, the objective function value of the current layout. Then we exchange 1 and 2, try exchanging 1 and 2, calculated it in the previous slide as 105. Then if you try to exchange 1 and 3, then the layout that you will obtain will be 3, 2, 1, 4. And when you calculate its cost value in a similar way, please do by your hand, by yourself. Okay, take a piece of paper and pencil and please calculate this. And you need to find this cost as 95. Similarly, exchange 1 and 4 and you will obtain this layout 4, 2, 3, 1. Okay, 4, 2, 3, 1. And when you calculate its objective function value, you again calculate it. You should find 120. Then exchange 2 and 3 and you will obtain 1, 3, 2, 4 layout. And its objective function value will be 120. Exchange 2 and 4 and you will get 105, and exchange 3 and 4 and you will obtain 125. So these are all the alternative exchanges, and among these alternatives you have to select the one with the minimum total cost, which is this one. Okay. And now what do? We compare this with the current one. And since this new cost 95 is less than 125, we say that okay, exchanging these two departments is beneficial and do it. And what are we exchanging? We are exchanging departments 1 and 3. So now our current layout is this new one after we find exchanging 1 and 3. Okay, 3, 2, 1, 4. And the cost of this layout is 95. Okay, this is TC current, the cost of the current layout. Now we don't stop at this point. Maybe after exchanging a number of some departments, a pair of departments in this layout, maybe we can find a better layout. So for that, again, we consider exchanging of the departments. Again, we need to exchange department 1 and 2, 1 and 3, 1 and 4, and need to calculate the total cost in the same way. The flow matrix will be the same, but the distance matrix should be adjusted. Okay, so with this given current layout, let's first calculate what happens if we exchange department 1 and 2. Okay, so the new layout then would be 3, 1, 2, 4. Okay, 3, 1, 2, 4. Now we need to calculate the distance for this layout and then multiply this distance matrix with the flow matrix to calculate the total layout. Again, please do this by yourself on a piece of paper and you should be able to calculate 105. Okay, then we need we need to consider exchanging 1 and 3 and we will obtain 1, 2, 3, 4 layout. In fact, this is the initial layout if you remember, and we already calculated its layout, its cost is 125. Then consider changing 1 and 4 and we will obtain 3, 2, 4, 1, which is 110. Then replace 2 and 3 and we will obtain 2, 3, 1, 4 with 90. And then consider exchanging 2 and 4 and then consider exchanging 3 and 4. Okay, so when we calculate all alternatives, we need to identify the minimum total cost, which is this one, and then compare this minimum cost with the current cost. And we see that the new layout or this exchange layout, which is 90, is less than 95. So we accept this exchange. Remember, in this alternative, we exchanged departments 2 and 3 and obtained 2, 3, 1, 4. And now we need to set the new layout to this one and try to improve it with further exchanges. So we start with this new layout 2314. Now our current cost is 90. The TC current is 90. And again, we need to consider all possible exchanges. Exchange departments 1 and 2, and you will obtain 1324, and its cost value is 120. Exchange 1 and 3 and you will obtain 105. Exchange 1 and 4, again you will obtain 105. 2 and 3 you will obtain 95. 2 and 4, we are not considering 2 and 1 again because we already considered while exchanging 1 and 2 here. If you exchange 2 and 1, you will obtain exactly the same one. Okay, so that's why we consider 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. Okay, and these are all the costs, and the minimum total cost is obtained by exchanging departments 2 and 3. And this cost is, when we compare it with the minimum cost, we see that the current cost is smaller than the exchanged cost. Then, since there are no other alternatives better than this one, we stop at this point. Okay, so this is the end of the algorithm, and the final layout is 2314 with an objective function value of 90. Remember, our initial layout was 125. Starting from this initial layout, we could improve it to 90. So this is the improvement. But as I said, this is a heuristic algorithm, and this 90, we don't know if it is optimal or not. Maybe it's not optimal. Maybe if we started from a different initial layout, we could find a better solution. Okay, but this is the main idea, main logic of the pairwise exchange method. So if we summarize the pairwise exchange method, this is a heuristic algorithm and it doesn't guarantee optimality. It just provides you a so-called local optimum, and this local optimum has no guarantee of being global optimum. It depends on your initial layout. Okay, so if you start from one layout, you end up with one final layout. If you start from a different initial layout, you may find a better or a worse solution. It depends on the initial layout. Okay, so in order to improve and in order to obtain even a better solution, you can repeat the same algorithm again and again. You start from an initial solution and find a layout. Then you start from a different initial solution and repeat the algorithm again. And you do this several times to obtain a better solution. It's also an option. And in one of the exchange, we have seen that when you exchange a layout, you may return back to an earlier layout. Okay, so it's possible to cycle back, and you need to calculate its objective function value again, and you lose some time here. But still, you need to do this. I mean, even understanding if it's an earlier layout consumes time. Okay, so you need to consume some time for already evaluated layouts. So this is a simple procedure. As we said, that pairwise exchange method can only be used if the department sizes, department areas are exactly the same. Okay, it's a simple procedure, but it's effective. It provides good solutions. Not, it doesn't guarantee optimality, but it provides good solutions. Okay, so this is the end of this lecture, and in the next one we will consider Craft and MC Craft algorithms. We will continue our discussion with improvement algorithms.